Now, the reactions we're going to talk about today are miscellaneous because, for the most part, they don't fit in the carbocation intermediate category that we've talked about. Remember, on Friday and Monday, we talked about reactions. We were adding HBr, HCl, HI, H3O+. Those all involve carbocations. The reactions we're going to talk about today, for the most part, don't involve those. Now, in fact, some of them don't even involve identifiable electrophiles. All right, so the first reaction we're going to talk about is catalytic hydrogenation. And this is a reaction actually we talked about back in Chem 14C when we talked about conjugation and aromaticity. We use the energy of this reaction to get a feeling for pi bonds and their relative stability. And so here's an example. Here's an alkene. We add hydrogen to that, and the two hydrogens, we get two new CH bonds at the expense of the carbon-carbon pi bond. Those two hydrogens end up on the same face of the alkene, on the same face of the molecule. So we call that a syn addition, like syn periplanar. That kind of syn addition, excuse me. Now, just from looking at the reaction and the hydrogen plus the alkene and figuring out the thermodynamics of this process, what we're doing is replacing a hydrogen-hydrogen bond, sigma bond, and a carbon-carbon pi bond, replacing that with two new CH sigma bonds. Now, without even looking up bond energies, I can tell you that this reaction most probably is going to be spontaneous, i.e., it has a delta G of less than 0 because, generally speaking, pi bonds are weaker than sigma bonds. Just to put some numbers on that, a carbon-carbon double bond is worth about 160 kilocalories if you rip that apart. 60 of that belongs to the pi component, and 100 belongs to the sigma bond component of that. So what we're doing here is replacing a sigma bond and a carbon-carbon pi bond, so that's weaker, with two stronger sigma bonds. So the net effect is we're giving up energy. But if you take an alkene and hydrogen and mix them up, they just sit there and look at them, each other. They do the 6th grade dance thing. Remember 6th grade dances? We used this metaphor before. You need to have something to come along to show the reactants, little Billy and little Jeannie in the 6th grade, how to, face each other and twirl around under the disco ball, that sort of thing. In other words, you need a catalyst because the process is too energetically expensive to do in its absence. So the hydrogen and alkene will react in the presence of a catalyst. Now, the catalyst will accelerate the reaction by changing the mechanism as catalysts do. And typically for hydrogenations, we use one of the platinum group metals, nickel, palladium, or platinum. Platinum is used frequently, palladium occasionally. Nickel gets used because it's cheap, but it just doesn't work as well, but it still can be used. And the thinking about how the catalyst works in this can also help us understand why the stereochemistry is what it is. Now, you do not need to know the mechanism for this reaction, but understanding the mechanism will help you think about why it is a syn addition. And if you'd like to know the mechanism, look in the textbook and or the Wikipedia under catalytic hydrogenation has some discussion of this. So here's how the mechanism works. The alkene and the hydrogen by themselves, as I said, just look at each other. But the metal, let's say platinum, will absorb the hydrogen. So on the surface of the metal, you end up with a bunch of hydrogen atoms attached to it. It's kind of like the technology they're talking about for hydrogen storing in hydrogen cars. You have a metal and it just absorbs the hydrogen on its surface. So if we imagine the bench up here to be the surface of the metal, when the hydrogen gets absorbed, you get a bunch of hydrogen atoms sticking up on its surface. Now the alkene will pick up the hydrogen by coming down with its p orbitals. These are p orbitals. I'm not making gangsta signs here. Right? And we can do an alkyne, too. Let's see if I can do an alkyne, too. That's an alkyne. All right. Sorry, it's about all I got today. So the alkene comes down with its p orbitals, and it plucks up those hydrogens one at a time, but almost simultaneously. In other words, so it comes down, plucks up one, and then this other one plucks a hydrogen. Now, because it's doing it simultaneously, the alkene doesn't have an opportunity to pick up one hydrogen, migrate away, flip over, and come back and pick up the other one. That would give you anti-addition. Doesn't happen. The collecting of the hydrogens is almost simultaneous. That almost simultaneous is going to come back to haunt us in a second. Now, what about the regiochemistry? By regiochemistry, we mean when the thing adds to the alkene, does it add in one direction or the other direction? So a good example of a regiochemical difference would be Markovnikov or anti-Markovnikov. So is catalytic hydrogenation, the example we have up here, is that Markovnikov or anti-Markovnikov? Remember, Markovnikov's rule doesn't talk about the nature of the mechanism. It simply talks about where the hydrogens from what we're adding end up relative to where the hydrogens were on the alkene to begin with. So is this reaction Markovnikov? Hydrogen adds to the end of the alkene that already has the most hydrogens. Is it anti-Markovnikov, like where the hydrogen adds to the end of the alkene that has the least number of hydrogens? Or is it neither or indeterminate? What do you think? It's neither. Markovnikov's rule doesn't apply here for two reasons. Number one, the alkene is symmetric. It doesn't have any hydrogens on it at all. So we don't know whether it adds this way or this way to the alkene. Can't tell. Number two, even if there was a difference, imagine this was methyl cyclohexene instead of dimethyl cyclohexene. So you have a hydrogen on one end of the alkene. We still couldn't tell whether the hydrogen adds this way or this way because it's hydrogen adding to each end of the alkene. So Markovnikov's rule, it's irrelevant here. It just doesn't apply. Now, what about the electrophile and the nucleophile in the reaction? Now, it's useful to think about electrophile and nucleophile because it can give us some sense of how the mechanism might happen. But for the mechanism that I described, the alkene coming down and plucking up hydrogens, there's no definite electrophile or nucleophile in that case. So this is the first reaction we've run across. We'll run across a few other ones, but where there is no distinct, identifiable electrophile or nucleophile. You can draw curved arrows, but there's really no identifiable, as I said, electrophile or nucleophile. All right, now, we'll talk about a little bit of an application of this kind of thing. Hydrogenation is used a lot in industry for a whole lot of things, among other things, processing food. One of the things that gets processed is unsaturated fats that are involved in things like vegetable oil and margarine and butter and that sort of thing. Butter has lots of unsaturated fats, that is, fats that have one or more carbon-carbon double bonds in them. And the problem with having unsaturated fats in your food outside of the health issue is that the presence of those alkenes allows the fat to go bad on exposure to oxygen more quickly. That's a free radical reaction. We'll talk about that later, about a week and a half or so when we talk about free radicals. So by doing catalytic hydrogenation and removing the carbon-carbon double bonds, you can get a product which has a longer shelf life. It's not going to go bad as quickly, so that's a good thing. Also, the presence of the double bonds, the more double bonds you have, the lower the melting point. And if you have butter on your table, it's not good that it's just liquid butter. It's kind of hard to spread on your toast or whatever. It's good if you have lobster, if you like lobster, but not so good for toast and things like that. So the idea is we're going to get rid of one or more of those double bonds, so it raises the melting point, and so we have a product that lasts longer. So we're going to do catalytic hydrogenation. Catalytic hydrogenation will knock out the double bonds, mechanism process we talked about up here. Now, if you want to knock out all of the double bonds, you want to convert your poly or mono or whatever unsaturated fat to a completely saturated fat, not a problem. What you end up with doesn't taste like much because it'll basically be Crisco. Crisco, the stuff, the white stuff, lard, that's essentially what you have left. Not very tasty. Certainly lasts longer because it doesn't have those alkenes. It doesn't have that issue with air oxidation. It has a higher melting point. Margarine is a good way to think of it. But it creates another health problem. This plucks up hydrogens almost simultaneously. This is where the almost comes in. Every now and then, couldn't put a number on it, maybe one molecule out of a million, I don't know. But every now and then, when the alkene comes down and plucks up the hydrogens, every now and then it plucks up one, migrates away, flips over, plucks up the other one, or plucks up one and then gives it back. And in the process of giving it back, the alkene can be converted from cis, which is the naturally occurring alkene 99.999% of the time in naturally occurring fats, and it can be converted to a trans alkene. And what do we know about trans alkenes in fats? It's bad for you. If you live in the city of New York, actually they're illegal now. The city of New York has banned trans fats in cooking oil. So that's where this stuff comes from. So when you hear about partially hydrogenated vegetable oil and that sort of thing, and they say, no trans fats. The only way there's no trans fat in there is if, number one, they've knocked out all of the double bonds. or they're kind of lying to you. And legally, they're allowed to do that, actually. Because when they say it has 0% trans fat, how many significant digits are there in the number 0? 1. So imagine you have 0.49% trans fat. What does that become when you round to one significant digit? 0. So legally, they're allowed to have 0.499999% trans fat and still call it 0. So be aware of those claims. I'm not mocking that industry. I'm just saying be aware that it's out there. All right. Next miscellaneous reaction we're going to talk about. Let's talk about the addition of halogens, Br2 or Cl2. And we'll use our same 1,2-dimethylcyclohexene. If we react that with Br2, bromine adds actually very quickly. This kind of reaction, if I demonstrated it up here, the color of the Br2, that's red, would go away basically as quickly as I could add it. And the net effect is we replace the carbon-carbon pi bond with 2 new carbon-bromine sigma bonds. So there's the thermodynamics of the process, very much like catalytic hydrogenation, except as it turns out we don't need a catalyst here. This reaction occurs very readily without much help. But the 2 bromines are added on the opposite faces, anti. So that suggests, first of all, the mechanism is different from catalytic hydrogenation, and it is completely different. What happens here is we end up with one bromine. The first bromine atom goes onto the alkene, forms a 3-membered ring with a positive charge, and then the second bromine has to come from the back of that in an SN2-like process. So that's why we end up with the anti. Again, you don't need to know the mechanism for that, but if you look at the mechanism either in the textbook or Wikipedia, it'll help you understand that a little bit better. So what about the reaction chemistry? Is it Markovnikov or anti-Markovnikov or neither or both? Well, it's certainly not Markovnikov. It's not anti-Markovnikov because there's no hydrogen involved at all here. So we really can't say which is operating. What about the electrophile? Well, the nucleophile this is a case we can identify a nucleophile. It's the alkene. The electrophile is the Br2 or the Cl2. Now you might say, wait a minute, how the heck does Br2 how does Br2 be an electrophile? After all, this is bromine, Br2. Same argument applies with Cl2. To be an electrophile, or at least to look like an electrophile, we said our molecule has to have, let me put in the lone pairs here, it has to have things like a formal positive charge. Is there a formal positive charge present here? No. Bromine with 8 electrons is neutral. There has to be an open octet. Both the bromines have 8 electrons. That's no good. What else does it potentially have to have before you can go and say, aha, that is an electrophile? It doesn't have a full positive charge. It doesn't have an open octet. Something else to look for. Delta plus. We saw a lot of these in SN2 reactions. So delta plus. Let's see, you get a delta plus when the bond is polar, when the electronegativity of the atoms is different. Okay, let's test that. What's the electronegativity of bromine? What's the number? That wasn't the question. You're right, but what's the question? What's the answer? 2.8 for bromine. And the electronegativity of bromine is 2.8. The point I'm trying to make, as you jumped ahead and so astutely pointed out, is because these atoms are identical, the bond isn't polar. So how does it become an electrophile? Here's how it becomes an electrophile. Here's our carbon-carbon double bond. The bromine is approaching and going, do I want to react with that or not? At a distance, the bromine looks at the carbon-carbon pi bond and goes, ugh. I'm repulsed by you. Why should the Br2 be repulsed by that carbon-carbon pi bond? Hint, imagine you are a Br2 molecule and the person sitting next to you is a carbon-carbon pi bond. Say hi to the person sitting next to you, but what do you see when you look at that carbon-carbon pi bond? Not on a pi bond, we see not a negative charge. Close. Electron density, the pi electrons. How do you think this bromine, remember this bromine is just basically a ball of electrons. How does it feel about other electrons? It feels repulsed. Electrons repel each other. And that doesn't mean that the bromine comes up, puts on the brakes, unless it's a Prius, puts on the brakes and then goes backwards. You know, Prius? Anybody here own a Prius? No? Nobody's getting their car recalled? You didn't hear about that? No, so on some cars with Toyota, it's the gas pedal. With the Prius, it's the brakes. Or excuse me, pre-I. That's if you have more than one Prius, pre-I. Anyways, so as these molecules approach each other, the electrons repel each other. What happens is the pi electrons cause a polarization in the bromine. These electrons kind of move away, they shy away, so we end up with a little bit of extra, with the electron density in the bromine-bromine bond is polarized. We put a delta plus towards the pi electrons, and then the pi electrons go, oh, now you look like an electrophile, and the reaction begins. So the Br2 becomes an electrophile because it's polarized by the presence of the pi electron. Same thing with Cl2 or I2 or F2 or any of those other kind of things that you might react with a carbon-carbon pi bond. All right. Now, here we're talking about Br2 and Cl2. They behave the same way. F2, actually, it's kind of difficult to do this with. It's kind of unreactive in that sense. And I2 will add to the alkene, but it's so reversible that it's just not practical. So really only Br2 and Cl2 are the practical ones. All right, middle of the page, we have another example of reaction to talk about, a process called hydroboration oxidation. And this is a way of adding water to an alkene, but unlike the alkene hydrations or alkyne hydrations we've seen up to this point, those were all Markovnikov. This one ends up being anti-Markovnikov. So the process is we take our alkene, and first we react it with BH3. That molecule is called borane. Not boring. Somebody once called it that on an exam. And BH3 is anything but boring, believe me. It's a gas at room temperature. If you expose it to the air, it spontaneously bursts into flame. You get a pretty green flame. So it's anything but boring. But that adds to the alkene in a syn manner. So the carbon-boron bond and the carbon-hydrogen bond are formed not only on the same face, but they're formed at the same time. And that's because as the BH3 comes down, this is boron and this is hydrogen, as they come down to bond with the alkene, they do so virtually simultaneously. And they have to do that on the same face, because it's a little difficult to make that four-membered ring transition state where the carbon in the, or excuse me, where the B and the H bond kind of straddles the alkene. Doesn't work very well. So they end up adding on the same face. You might say, well, then how about the BH3? How is that electrophilic? Well, it's got, what does BH3 have that would make it electrophilic? Let's see. Does it have, since we just talked about a delta plus, does BH3 have a delta plus in either boron or hydrogen? What's the electronegativities involved? Hydrogen, we know. What's the electronegativity of hydrogen? 2.1. Let's take a guess on boron. There's boron up there in your periodic table. If you start with fluorine is 4, oxygen's 3.5, nitrogen is 3, carbon's 2.5, boron is 2.0. 2.3 is not a bad guess, but 2.0 is what it is. And so would a bond between hydrogen, electronegativity 2.1, and boron, 2.0, be polar? No. It's also a very short bond, because it's a first row and a second row element. So virtually no polarity in the BH bond. So there's no delta plus, delta minus there. What about formal charge? Does BH3 have a positive formal charge? Hint, look at the structure, which is correctly drawn. If you're not sure, calculate what the formal charge should be based upon the number of electrons. It's neutral. So that's not the issue. But the number of electrons is the issue. What is it about the boron and BH3 which makes it an electrophile? Doesn't have a full octet. It's not playing with 8 electrons. It's a little, it's not playing with a full octet. No? Okay. It's like, I guess the chemistry 14D version of that is you're a little, you come to the exam without a full model kit, that means you're crazy. Right? You've heard not playing with a full deck, right? Not taking the exam with a full model kit. That would be... I told you this thing before was the best I had today. Can you insert a laugh track today? Can you do that? All right. So anyway, so the BH3 is an electrophile because the boron has an open octet, and it adds to put the hydrogen on the more substituted end and the boron on the less substituted end of the alkene. So is the BH3 addition Markovnikov or anti-Markovnikov? Does the hydrogen of the electrophile go to the more or less substituted end of the alkene? It goes to the more substituted end of the alkene. So this addition is anti-Markovnikov. But we're not done because we're really not interested in the carbon-boron bond in the product. It turns out not many molecules that are the kinds of things that we might consume as consumers, as pharmaceuticals or dyes or stuff in gasoline or whatever. Not too many of those things have carbon-boron bonds in, but carbon-boron bonds are really, really, really useful. As a matter of fact, with the appropriate set of reactants, you can convert a carbon-boron bond to almost any other functional group you'd like to, which is why the hydroboration strategy is so useful. But we're particularly interested in the oxidation portion. So the carbon-boron bond is then oxidized with hydrogen peroxide and base, sodium hydroxide. That converts the carbon-boron bond to a carbon-oxygen bond, and in a way that retains the stereochemistry at that carbon. So the net effect of the entire process, we've added that molecule of water, there it is. We've added it in an anti-Markovnikov sense, and it's a syn addition. But it's not water itself that's undergoing the reaction. It's the borane, which then gets oxidized. Now, I want to point out something about this. This is really a two-step process. So we put in the BH3, and only when that's done do we put in the hydrogen peroxide and the sodium hydroxide. When we have those kind of reactions, we routinely write them with this 1-2 notation. That means put in the stuff that's in step 1. And when it's completely done, when it's done reacting, when you're out of curved arrows that you can draw, then you go to the stuff in step 2, and then the stuff in step 2 operates. It's assumed here that either, when you get to step 2, that either the stuff in step 1 has been completely used up, or the stuff in step 2 destroys the stuff in step 1. Either way, once you've moved on to step 2, step 1's in the past. You don't think about it anymore. It's like after you've been divorced and you're going on a date to find your new significant other, you don't talk about what you did in the past. Usually that's not going to a second date if that kind of thing happens, right? So this is in the past. We don't talk about it. We forget it once it's done. All right, so we've talked about all the stuff here on the bottom. Now, I do want to point out this particular process, while it is a way of making alcohols, as I said, you can convert that carbon-boron bond to almost any other functional group you want. And the development of these reactions by a guy named H.C. Brown, who was at Purdue University, he passed away a bunch of years ago, was so important to synthesis and industry that actually he shared the Nobel Prize in 1979 for the development of this kind of chemistry. All right, on the bottom of the page, we have our last miscellaneous reaction that we talk about before we segue into our biological reactions, and that is ozonolysis. The name literally means ozone breaking. Lysis, breaking apart. You life science majors know all about lysis of cells. Right? If you get a divorce, that's like a family unit lysis. All right, never mind. Lysis, breaking. All right, so this is ozone breaking. Here's an example. Here we have, this is styrene actually, the stuff that's used to make polystyrene. And when this reacts with ozone, so this is one of those 1-2 reactions. First we react with ozone, O3, and then we react in this case with dimethyl sulfide, 2 methyls on a sulfur, stuff that, by the way, smells like rotting garlicky tomatoes. What that does is that chops the carbon-carbon double bond. So conceptually what we're doing is taking this carbon-carbon double bond, chopping right through the middle. And a 14D student once said, oh, I know how to remember this reaction. Ozone is like the surgeon's scalpel. That does the cutting. And then what I'm going to do, so we've cut, and then we're going to suture the wound here, or cauterize the wound with the oxygen so it doesn't bleed anymore. Whatever works for you, if that's a way for you to remember it. You might go, wait a minute. We're talking about addition to carbon-carbon pi bonds. This doesn't look like an addition reaction. This looks like a chopping apart carbon-carbon double bonds reaction. Well, initially it is an addition. The mechanism, again, for which you are not responsible, the mechanism begins with alkene and ozone coming down and adding to it. You end up with a 5-membered ring, which is carbon-carbon, oxygen, oxygen, oxygen. So the initial step in the mechanism is an addition. But then there's some bond breaking and some rearrangement and so forth that happens. Again, textbook and or Wikipedia can go through the details of the mechanism for you. But the net effect is chopping completely through the double bond. You can even do this with triple bonds, and you end up with carbonyls. Now, if we wanted to talk about the overall stereochemistry, remember addition of Br2 and Cl2 was anti, hydroboration is syn, ozonolysis is, well, initially it's a syn addition. The first step is syn, but the product has no stereochemistry whatsoever. That's completely gone, so we can't say. So the stereochemistry really overall is none. What about the regiochemistry? Markovnikov, anti-Markovnikov, neither. Hint. Does O3 have any hydrogens in it? No, maybe you've noticed by now that Markovnikov's rule is a statement of how HX adds to the pi bond, and since O3 doesn't have any H, Markovnikov's rule simply doesn't apply. Now the electrophile, we might think of the ozone as the electrophile. It turns out if you draw out the mechanism, it's not, because when you draw the curved arrows, the ozone is both accepting and giving up electrons. So it's hard to identify it as the electrophile. But if you go into the laboratory and you study different alkenes that are more electron-rich, i.e. more nucleophilic, react faster. So ozone kind of behaves like the electrophile, but formally it isn't. So we're going to say there's really no electrophile in this reaction. Now, let's talk about biological reactions. Biological examples. There's lots and lots and lots of biological examples. I mean, some of these things obviously aren't going to have biological equivalents. For example, you don't have Br2 running around your body, I assume. If you do, you're probably dead. Br2 is pretty powerful. It reacts with lots of things. That's probably not there. But ozone, on the other hand, while it may not be much inside you, it's certainly around you. After all, this is, for those of you out there in YouTube land, this is Los Angeles. And if there's one thing we have in Los Angeles, it's ozone. So why should that be of a concern? Well, ozone reacts with carbon-carbon double bonds. And there are carbon-carbon double bonds all over the place. For example, there are some in windshield wipers. The rubber in your windshield wipers has carbon-carbon double bonds in it. Now, those of you from out here in Los Angeles are used to replacing your windshield wipers about, once a week? Those of you who are from the East Coast, any East Coast people here? Am I the only one? Okay, well, I will tell you, on the East Coast, windshield wipers last 2 years, 3 years. They don't get brittle quickly. That's because there's not nearly as much crap in the air to chew up the rubber on them. There's not much ozone. So let's talk about it in a different way, something we would all relate to, and that's carbon-carbon double bonds in the lungs. There's a group of molecules in the lungs called pulmonary surfactant. And surfactant is a shortened term for surface active agent. And what these group of molecules do is they reduce the surface tension in the mucus in your lungs and make it easier for oxygen to move from the air into the bloodstream. Now, to have the surface active effect, to have the reducing surface tension effect, the molecules need to have large nonpolar areas as well as large polar areas. And so that's why the molecules look typically like this. It's not one molecule, it's a group of related molecules, but this is a good example. These are phospholipids. If you remember back to 14Z, phospholipids. There's the glycerin. There's the 1, 2, the long fatty acid chains, and then there's the shorter end. But the phosphate, the positive charge, and the nitrogen, the esters. That's the polar portion. And then we have 2 large nonpolar portions. Now, to put this in perspective, this kind of drawing it this way underemphasizes how much non-polarity there is to this molecule. You're really talking about long carbon chains with lots of non-polarity there. But it is the amount of non-polarity. It's having lots of non-polarity that matters. So what happens when you breathe in ozone? Well, if there is a carbon-carbon double bond, the ozone can chop that carbon-carbon double bond. Under biological conditions, it turns out it makes carboxylic acids instead of aldehydes and ketones, but it still chops that carbon-carbon double bond. And in this particular component of pulmonary surfactant, when you lose this guy over here, you're losing about 1/4 of your total non-polarity. And that decreases significantly the ability of this molecule to have its surface active effect. And when you don't have that effect, it becomes harder to breathe. Now, part of the problem with this also is that these molecules are not replaced all that quickly. So if you breathe in a lot of ozone, the surface active effect can be reduced pretty quickly. All right. Now, let's talk about a different example, and that is biosynthesis of steroids. Remember, steroids have a typical 6-6-6-5 ring arrangement, and we talked way back in 14C just very briefly about where steroids came from. Well, now we're going to talk about it in a little bit more detail. And the whole process, and I'm going to use this, by the way, as an example of a number of things. We're going to talk about addition to carbon-carbon pi bonds. We're going to talk about Markovnikov's rule. We're going to talk about carbocation fates, etc. I do not expect you to memorize structures, to be able to reproduce the entire mechanism from memory. Don't need to do that. What you should be able to do, though, is look at any individual step, draw the curved arrows for it, understand essentially why it's happening this way as opposed to some other way. If something unusual is happening in that step, try to identify, well, this is unusual, and maybe think about why that is. So the whole process begins with this molecule, which is called acetyl-CoA. And acetyl-CoA is a 2-carbon building block. So the methyl group and the carbonyl of this thioester, the S-CoA is a leaving group based on sulfur, those elements, those carbons are put together to build bigger molecules. It's used for fatty acids and that kind of thing. So in the steroid case, a bunch of these are put together to make this guy, which is called squalene. Now, squalene has enough carbons to build the steroid, but it certainly doesn't have the right functional groups, because the only functional groups that are present here are alkenes, and it's clear we need to build some new carbon-carbon bonds to make that steroid skeleton. So our only functional groups we have to work with are alkenes. Have we seen any reactions where two alkenes come together and make carbon-carbon bonds? Well, let's see. How would that work? Alkenes are nucleophiles. So that would mean this nucleophile, this alkene, plus this nucleophile would have to come together. Do we know any reactions where two nucleophiles come together? No, nucleophiles react with electrophiles, not other nucleophiles. So the squalene by itself is not in a position to make new carbon-carbon bonds. So what we need to do is convert one of those alkenes to a functional group which is electrophilic, one that has a leaving group. And Mother Nature does that by reacting an alkene on the end with oxygen in the presence of an enzyme called squalene epoxidase, and that makes this 3-membered ring ether, which is called an epoxide. Now, ethers, although we don't really talk about ether chemistry in here so much, ethers by themselves are pretty unreactive beasts. They don't have leaving groups, they don't have acidic hydrogens, so they tend not to do a whole lot. They're kind of boring, actually. But this particular kind of ether, on the other hand, has something that makes it a little bit more interesting. Why is this? What's special about this 3-membered ring? What do you think? Ring string, yeah. It would like to pop open and relieve that. So you can imagine this breaking in a way that the carbon-oxygen bond breaks and the electrons go to the oxygen. In other words, you have an O- leaving group. So you can imagine this kind of process happening, let's say like that. And then you'd end up with a positive charge on the carbon and negative charge on the oxygen. Well, what do we think about? So the leaving group then is RO-. What do we think about RO- as a leaving group? Is it excellent leaving group, moderate leaving group, sucky leaving group, only leaves under special circumstances, never, ever, ever leaves? It's beyond sucky. RO-, can you use hydroxide, for example, or methoxide as a leaving group in an SN2, SM1, E2, or E1 reaction? Nope. RO- only leaves under special circumstances that we have yet to define, and I'm here to tell you, folks, that this is not one of them. So even though there is ring strain, that is not enough to overcome it, principally because, well, why is RO- a lousy leaving group? It's got ring strain to help it here, certainly, but something works against it. Well, it's atomic radius. That's true. That's one of the things that works against it. Electron density, you were going to say it's not stable. Can you be a little more specific about the not stable issue? It's kind of related to the electron density. Somebody dropped the F-bomb over there. Oh, come on, say it louder. The First Amendment allows you to drop the F-bomb as loud as you want. Formal charge, right. That's one of the allowable F-bombs in here. Formal charge and functional group. So if you get really frustrated in the exam, stand up, throw your pencil down, and go, functional group. So formal charge, it goes from being neutral to negative. Well, that's bad. But wait, we know how to get around that. If you have an oxygen that's neutral to begin with, and it would leave and become negative, and that's bad. We would like for it to be neutral when it leaves, which means before it leaves it should be positive. How have we made oxygens positive? Protonated them. Mother Nature's way ahead of you. She studied 14D, she knows that trick. So even though the epoxide has ring strain, it's not good enough, the ring strain by itself is not good enough to allow it to open in the presence of weak nucleophiles. It turns out strong nucleophiles can attack epoxides, but we're not going to worry about that right now. So we put a proton on, and that gets done with an enzyme. So there's our protonated epoxide, and now the combination of positive charge in the oxygen plus ring strain, now it can pop open. But it can pop open one of two ways. There's two CO bonds, and when it opens up, it's going to make a carbocation. Here, it opens up in a way that makes the tertiary carbocation. If it opened the other way, the carbocation would be, if the CO bond that's not shown being broken here, if that broke, the carbocation it produced would be secondary. If you've got a preference, which do you make, secondary or tertiary? Tertiary. So it opens up to make the tertiary carbocation. Now that word carbocation should immediately make the little voice in your head say, every time I see a carbocation in a reaction mechanism, regardless of where it comes from, here it comes from ionization of a carbon-leaving group bond, we think about resonance first. Resonance not an issue in this particular case. The next thing we think about is three-phase. Well, we're trying to make carbon-carbon bonds, and there happens to be a nucleophile here. Not a great nucleophile, but it's still a nucleophile, so let's capture a nucleophile. And that's going to build this carbon-carbon bond. Or you can think of this as electrophilic addition to a pi bond, where the electrophile is a carbocation. Either way, they're semantics. The words mean exactly the same thing here. Now, this is an unsymmetrical pi bond, and we know that when you add an electrophile to an unsymmetrical pi bond, you add it in the way, if it's going to make a carbocation, you add it in the way that makes the more stable carbocation. So here, your choice is you can make the new bond here as shown that makes a tertiary carbocation, or if you made a bond between this carbon and the other alkene carbon, that would put the positive charge there, what kind of carbocation would that be? Secondary. Tertiary is better. So that's why we get a six-membered ring. That's part of why the A ring, that's that first ring in the steroid, is a six-membered ring. But it generates a carbocation. Resonance, right? Every time you see a carbocation in a reaction mechanism, regardless it comes from, in this case it came from electrophilic addition to a pi bond, resonance. Is there resonance? No. What do? Three-phase. What should we do? Capture a nucleophile, because we're trying to make carbon-carbon pi bonds. Exactly the same, or carbon-carbon bonds. So exactly the same thing. Capture the nucleophile, make a new carbocation, our choice is secondary or tertiary, so we pick tertiary. I was going through that quickly, because it's exactly the same thing we just did. Now we have a carbocation. Resonance. Getting kind of repetitious, isn't it? Every time you see a carbocation, resonance, yeah, right. So add the nucleophile. Wait a minute. Carbocation that we've made here is methyl primary, secondary, tertiary? Secondary. Is that the best possible carbocation we could make in this mechanism step? No, we could make a tertiary. Now, this is one of those times where you look at this mechanism and go, this is really what's happening. I'll tell you we know that. But what's going on? This looks to be what we will call contra-thermodynamic. It's not the most thermodynamic stable possibility. Well, what's happening here is remember that when this thing folds up, it doesn't, number one, it doesn't happen all by itself in the gas phase. There's stuff around it. In this case, there's an enzyme. And the enzyme is controlling the way the molecule folds up. It controls its conformation. And it is apparent in this particular step of the mechanism that the alkene is held in a way that only one end can get close to the carbocation. It's not like the carbocation is a choice. Only one end of the alkene is presented. That's where the bond is made. Now, it's also probable that the way this mechanism is written with the individual carbocations, it probably really isn't happening that way. Probably all the bonds are forming simultaneously, and that gets around this issue. But nonetheless, the enzyme controls the conformation of what's going on. But we still get a carbocation. There's another pi bond to add to, so we add this time to make the tertiary carbocation. And at that point, Mother Nature says, okay, I'm sick of adding to pi bonds. Let's do something else. Why don't we add to this pi bond out here? The enzyme holds it away. So Mother Nature says, okay, I've done adding to pi bonds. Let's do something else. Let's do other carbocation fates. Let's do some rearrangements. So we're going to rearrange, shift the hydrogen. Remember, the rules are you can shift CC or CH bonds, and they have to be adjacent. So this CH bond is adjacent to the positive charge, and that moves a tertiary carbocation to a tertiary carbocation. And you might say, what's the point of that? Aren't rearrangements supposed to make the carbocation more stable? Well, that's what most of the rearrangements that we see do, because those are highly favorable rearrangements. But rearrangements are equilibrium processes. So carbocation A and carbocation B are in equilibrium. If carbocation B is more stable, then the rearrangement looks like it makes it more stable and it doesn't really go backwards. But you can go from tertiary to tertiary. Heck, you can go from tertiary to secondary. It's possible. Tertiary to secondary just isn't very probable. And there may be other things that cause subtle differences in the stability between this acyclic tertiary carbocation and the cyclic tertiary carbocation. Maybe there's something in the enzyme that's kind of hanging electron density over that one carbon saying, come on, put the positive charge over here. You'll be a little more stable because there's electrons over here. We don't know that, right? We're being very simple. But it happens. So we're going to do, now we do a methyl shift, and then we do a methyl shift, and finally Mother Nature says, I'm bored of carbocation rearrangements. I've done rearrangements. I've done capture a nucleophile. What's left? Lose a proton. See, Mother Nature studied 14D. She knows all about this stuff. By the way, she did pretty well. She's really good at synthesis. So once we get up to here, then we do the deprotonation. In this case, we're using the enzyme to do the deprotonation. What do we know about the basicity of the enzyme here? We know nothing about the basicity of the enzyme. We only know that the enzyme is doing it. I don't know what site on the enzyme is doing it. But does that really matter? Because we're deprotonating a carbocation. Does the enzyme have to be a strong base to do that? No. And as a matter of fact, it is quite possible that the site that's doing this deprotonation in the end is the one that puts the proton on here. That would complete the catalytic cycle. Maybe. All right, so that takes us up to linesterol. We've built the 6,6,6,5 system, but we're not done. Because the biological precursor for mammalian steroids is cholesterol. If we were a plant, we might be done, but we're not a plant. We're doing mammals. So we have to go from linesterol to cholesterol. And you can see some of the changes that are involved. We have to get rid of these methyl groups on the A ring. We have to migrate the double bond. We have to get rid of the alkene in the side chain. There's a bunch of things to do, and that takes about another, 25 or 30 enzyme steps to actually carry that out. And that takes you down to cholesterol. And from there is where you make all your other steroids from. So whatever it is you need, testosterone, estrogen, bile acids, whatever you need, you make them all from that guy. Now, I want to emphasize, again, people ask at this point, do I have to memorize this? This is 2 pages of stuff. And the answer to that is no. I'm not going to ask you to draw it out. However, again, you should be able to look at any given step in the mechanism and draw the curved arrows. If something strange is happening, like this one case where we close the ring to make the secondary carbocation when a tertiary might be possible, to point at that and say, this is a little unusual because, in this case, because it's making the less stable carbocation. Those are the kinds of things that we would like for you to do. All right, so that ends our discussion of addition to carbon-carbon pi bonds. On Friday, we'll start talking about electrophilic aromatic substitution, somewhat related to this topic. Need your think book for that, so bring that along on Friday. See you then.